All right, Taylor's theorem from calculus says that any curve can be approximated locally by a low degree polynomial. And another theorem called Weierstrass's theorem says that any function can be approximated globally by a high degree polynomial. So we've got locally and globally, low degree and high degree, polynomial and polynomial. So this vignette is all about finding the sweet spot, polynomially speaking, somewhere in between. Okay, so we're going to be approximating noisy xy relationships with a polynomial. So the model is going to be that our response yi is a linear function of xi through additional powered up versions of x. So look how I created extra slope coefficients in front of powers of x. Technically, this is a multiple linear regression, which is what I'm going to talk about in the next vignette. But this is a very special multiple linear regression where the features are powers of x. Okay, so let's not talk too much about multiple linear regression and save that until next time. You can choose to power up as much as you'd like. But be careful. Why? When you have less data than the degree of the polynomial, where d is the degree of powering up, you get a perfect fit. I'm going to put perfect in quotes because the polynomial interpolates all points. That means it goes through all of the points. But that perfect fit is not ideal, which I will also put in quotes, since if you're interpolating, all of the epsilons are 0 for all I, which isn't Gaussian. In fact, it doesn't have a distribution at all. It's not at all random. And so it violates the key modeling assumption that your epsilons are IID Gaussian. So this is known as, these two things together are describing what is known as overfit. Fortunately, you can check if you need degree D by testing if the coefficient in front of the dth degree is equal to 0 or not through a hypothesis test. All right, that is all of the writing that I'm going to do for this vignette. The rest of it is going to be our code. So we're going to play around with this idea with data that you can find in the NMLE package. Don't forget to install .packages NMLE, which you need to do once per computer. And then after you do that, you can load in this soybean data. And we're going to look at, there's a lot of interesting stuff in this data set, but we're not going to look at all of it. I'm going to just look at soybean time less than 65 and soybean variety of P. So we're looking at a subset of the data and variety equals P, calls not found. Plot variety year time. Oh, I put a comma instead of an and. Okay, there you go. So let's look at the data. So we're going to plot soy time on the x-axis and soy weight on the y-axis, and I got to make sure you can see that. Okay, so here is the situation. We clearly have a non-linear relationship between x and y, and also we have some bunching. We clearly have bunching on the y-axis. We may also have bunching on the x-axis, but thinking about x's is what this vignette is all about. So I'm only going to transform one of the two variables. I'm going to use what we did in part A, and I'm going to take for my y the log of soy time, and then as my x is going to be soy weight. Okay, and so new visual on transformed scale. Okay, so clearly, I didn't, oh no, I did it right. Oh, I see what I've done. I've inverted the x's and y's. It should be soy, log of soy weight. Weight is the output, and time is the input. Sorry, I totally messed that up. Okay, that looks way better, right? We don't have as much bunching in the y-axis, and actually it's clearer now that we don't really have bunching in the x-axis either. And I can do a fit. I can do an L fit, LM y twiddle x, and then AB line L fit. And there is the fit to that data. And maybe it's clear that there is some relationship left over. Let's see, let's look at residuals. Plot x L fit resid, AB line h equals 0. I think that this isn't a great fit. In fact, what I see is kind of a parabola. I've got a parabola left over in my xy relationship. And so I'm going to try to resolve that misfit with a polynomial regression. So here's how you do that. I'm going to make a new x that is the square of the original x. And then I'm going to fit my regression for y given x and x2 added together. Okay, so this is how we fit a multiple linear regression, but the features of that multiple linear regression in this case are just powers of the original x. Okay, so was that a good idea? Well, we can always look at the summary of the fit and of the second fit and see that this new predictor has a test statistic for the null hypothesis that the coefficient is 0, which is very large and leads to a small p-value. So small p-value, I'm trying to write up here, on the null hypothesis that beta 2 is equal to 0 rejects that null hypothesis. So we know that the degree 2 polynomial is a good idea. Okay. So let's look at the fit that we got. So let's go grab this x and y. Right, we made that plot before. We need a predictive grid. So x is sequence from min of x to max of x, length equals 1,000. And then we got to make x2s. So that's, oh, I shouldn't have called that x. I should have called that xp. Got to be careful here because I don't want to write it over the x that I'm already doing. This is xp. This is xp2, which is xp squared. And then I can predict using lfit2 new data equals data frame. I'll give it the x's, but I'll also give it the x2s. So those are the locations I want to predict at. Okay, now I can do lines and only put in the xp's here. The xp2s are felt through the prediction, but I only want to make a plot that has x on the x-axis and y on the y-axis. So I'm only putting the x's in, but I'm going to take the first column from the prediction. And look how that has curvature. It has curvature because the coefficient in front of the squared predictor is negative, so that's concave down. And then I can add on the other lines that provide the prediction interval. There's the lower one and the upper one. Okay, so really good fit now to the logarithm of the response. So now we can put everything back on the original data scale. So if we just plot soybean, or I guess it was soy weight and soy time. Was it capital W in weight? I can't remember. No, it's lowercase w. So there's the original data. And now I want to take these predictions and then exponentiate them to put them back on the original scale of the data. But that did not do anything. Oh, it's time, and I did it again. It's time and then weight. Yeah, I just need to go a little slower. Time and then weight. Now my line will go on there, and I can grab these two as well and exponentiate the predictions to put them back on the original scale of the data and get these really nice prediction intervals, and I get all the benefits of having transformed with the logarithm and back transformed with the exponential. I'll never predict a negative weight, because negative weights don't make any sense, and I get really nice nonlinear predictions. So I've combined two things into this analysis. I use transformations through the logarithm of y, and I've used polynomials through powers of x. And I can check if I need even higher powers. Right? I can make an x3 that is x cubed, and then I can go look at the fit that I get from y and x squared and x cubed. And then, oh, I didn't run, oops, I called that x2. I've got all sorts of typos. Better go back and make sure that x2 is what it's supposed to be, and that x3, and then I can do the fit, and then I can do summary, lfit. I should call that lfit3. And I should probably make sure that I rerun that as well. So lfit3 has the cubic. And then look, the x3 predictor has a very small t-statistic and large p-value, so I cannot reject the null hypothesis that beta 3 is equal to 0. So I conclude that a degree 2 polynomial is sufficient for modeling these data. So there you go. Polynomial regression involves doing a linear regression with new features that are derived from powered up versions of the original predictor, x.